Hello and welcome back to Exam Ignite. In this video, we are starting Module 3, Part 1 of Principles of Communication System for the VTU syllabus, 4th semester under the 2022 scheme. As always, I have prepared the notes as easy to understand handwritten notes with the focusing on the important questions and the expected questions. So this here I will be covering the VTU syllabus with the model question paper 1 and 2 with the previous year question paper Jan 2025 and July 2024 question papers. So I have marked the questions I have marked where the topic has been appeared in the previous year papers. So stay till the end and let's begin with the module 3 part 1. The fundamentals of the frequency modulation. Here we are going to study about the basic principles of frequency modulation, principles of phase modulation, modulation index and sidebands, noise suppression effects of the frequency modulation, frequency modulation versus the amplitude modulation. Also, a method to convert the PM to FM signal and FM crystal oscillator, FM vector oscillator under this frequency modulation. That is second part, frequency modulation circuits. Here VCOs, that is voltage controlled oscillators, very important one. Frequency demodulators, then slope detectors and phase locked loops. That is a very important one. Communication receiver, it is a super heterodyne receiver. Frequency conversion, mixing principles and JFET mixer. This frequency circuit part will be discussed in the part 2 of the video and part 2 of the module 3. I am going to discuss only this first part. Let's get started. Firstly, you need to know the fundamental, that is a sine wave carrier can be modulated by the varying the amplitude, frequency and the phase. Carrier wave equation is given as V is equal to Vc sine 2 pi ft plus or minus theta. PM and FM, these are the angle modulation. PM is phase modulation and FM is frequency modulation. PM is varying the phase shift of the carrier and FM is information is impressed by the changing the frequency of the carrier. Basic principles of FM. In the FM carrier, this is the first topic, FM carrier. Carrier amplitude remains constant and FC varies by modulation signal. FC shifts proportionally with the amplitude of the information signal. That is, if the modulation signal increases, then the frequency of the carrier also increases. If the modulation signal decreases, then the frequency of the carrier signal decreases. FC varies above and below its center frequency depending on the amplitude of the modulating signal. Amount of the frequency change, that what changes happen, that we will call it as frequency deviation, that is FT. These terms are important. You should know what are these. That is maximum deviation at the peak amplitude of the modulation signal. We can observe the maximum deviation. Then modulating signal effects, the frequency determines the deviation rate, that is 500 Hz. And then the modulating sine wave causes a frequency deviation of 500 times per second. This is a carrier signal. This is a modulating signal and this will be our FM signal and this will be our PM signal. This is a problem, basic simple problem, you can refer to it. Next is frequency shift keying, that is when used when modulation signal is pulse train or the binary data. Modulation signal has two amplitudes, that is what, 0 and 1. 0 is carrier stays at the center frequency. 1 means carrier stays at the higher frequency. Carrier has only two frequency values, unlike the analog. Analog has many, but here either it will be 0 or 1. You can observe the waveform here. It is used in the Bluetooth headsets, wireless speakers, industrial wireless communication system. Next is the principles of phase modulation. Here, PM, that is a constant frequency carrier, phase shifted is varied in accordance with the amplitude of the modulating signal. A modulator circuit causes a time separation, that is a phase shift between the two sine waves of the same frequency. So the phase shift varies with the amplitude of the modulating signal. That is, if it is a positive amplitude, then it is a lagging phase shift. If it is a negative amplitude, then it is called leading phase shift. Output of the phase shifter is a PM wave. Positive modulating signal will increase the phase delay and hence what appears like a lower frequency. Negative modulating signal, it is a leading phase, as I said, appears like a higher frequency. Frequency modulation is produced temperature during the changes in the phase shift, that is only when modulating signal is varying. The modulating signal behavior in PM and FM you can observe. This is the modulating signal. This is triangular waves with the clipping ends. It has got clipped here. You can observe it has got clipped. Next is FM. This is how FM is, and this is how PM is. PM is what frequency deviations happens only when the modulating signal changes. Maximum deviation occurs when the rate of change is highest at the zero crossing for the sine wave. In contrast, FM deviation is maximum at the signal peaks, not at the zero crossings. In PM, that is phase modulation, maximum deviation occurs at the message signal changes rapidly for the sine wave. This is at the zero crossing points. Now we will learn about PM, that is frequency deviation is directly proportional to a change of rate of modulating signal, which is a derivative. It behaves like a cosine of the sine wave. Uh, Frequency deviation, you can see it is directly proportional to amplitude and directly proportional to frequency. What? This PM. But when it comes in the case of FM, FD is on directly proportional to amplitude only. So the relationship between the modulating signal and the frequency deviation you can observe here. As for the PM and FM, both the modulating signal, it depends on the amplitude of both. Like FM and PM have directly proportional to amplitude, so therefore we get a slope like this. But in the case of frequency, for the modulating signal frequency, PM only varies, but FM is constant. So converting a PM to FM, this was asked in the model question paper 1 and July 2024 paper. How to convert PM to FM signal. So PM, this is a very important one. So PM can simulate FM using a low pass RC network, that is pre-directors or the 1 by F filter. So increasing the frequency, modulating signal can cause greater FT. So filter reduces their amplitude, ensuring the PM has a deviation like FM. So using a LPF, that is low pass filter, to roll off the audio message signal with the frequency, we do like this. Here we provide the signal using the microphone, using a microphone that is sent, and here we are having an amplifier that gets amplified using the RC circuit is also there, that is sent to the phase modulator. We give a carrier oscillator, so we get an indirect PM. So here, sorry, FM indirect. So here PM is sent and we get an indirect FM. What happens here is there is a roll off of the audio signal with an increase in the frequency. So that is what observed here in the graph. Next is phase shift keying. This is a concept under this where PM used with the binary data, PSK or the binary PSK. So binary means 0, that is 0 volts. Binary 1 means 3 volts. Either this or this. This is carrier at the reference point. This is carrier with a 180-degree phase shift. You can observe. So here it is 1 and here it is 0. When we change it to the waveform, here we can observe there is a 180-degree phase shift here at this points. Next is each binary transition occurs 180-degree phase shift, no frequency variation, only phase changes here. So either the phase values are 45, 90 or 135 degree can be used in the PSK methods. So next is modulation index or the sidebands. Based on this, you can expect a problem. Each modulation frequency creates a pair of sidebands, that is USP is equal to what? FC plus N into FM. LSP is equal to FC minus N number of FM. So more deviation means more sidebands, that is wider sidebands than the AM. So modulation index of the frequency, it is given by FD divided by FM. Deviation ratio is FD maximum divided by FD minimum. Then Bessel function in the FM, this is also used in a problem. So just go through this if you need a concept to understand the Bessel function. Based on that, there will be a formula. For that, you need to do for a problem. Next is method 1. Using the number of SP, we are having two methods to find the FM bandwidth estimation. We are having two. One is bandwidth is 2 times the FM into N, and N is the number of significant sidebands placed from the table. And method 2 is our Carson's rule, where bandwidth is 2 times the FT plus FM. So based on that, there is a small example. Refer that. Then FM with digital or a pulse signals, a square wave contains a fundamental plus odd harmonics. So each harmonic has an extra sideband, so filtering is needed to limit the harmonics and reduce the bandwidth. Noise suppression effects of FM. This is also the most important topic in this module in the part 1, where noise is caused by the external interface such as lightning, motors, ignition system, or you can say power line switching in various ways. So they usually narrow high frequency voltage spikes within the communication signal. So FM signals have a constant carrier amplitude. Limiter circuit in the FM receives the clip amplitude variation, effectively removing the noise. So you can observe here the noise spikes are like this. This is the amplitude variation above this level is clipped off above this part, and the FM is allowed to pass FM signal. So this is what waveform denoting the FM with noise. And here also the amplitude variation above and below are clipped off. Since the FM information is carried by the frequency changes, not the amplitude, only frequency changes. Clipping the amplitude does not affect the signal content. So FM has a superior noise immunity compared to AM. This is a major advantage of FM. So demodulation process itself suppresses noise, improving the signal to noise ratio. This is also one more advantage. Noise and phase shift. Here noise introduces a small phase shift or a frequency deviation in the FM part. So by the phasor diagram representation, you can say we are having two phasor diagrams. Consider this as S, C and N. So N is our noise phasor, C is our composite phasor, and S is a signal phasor. So we can define the phi, that is a phase shift angle, as sine inverse of N by C. Okay, so next by the phase shift angle we got the formula. Now frequency deviation due to signal, it is given by delta is equal to phi into FM. Based on this you can expect the formula. This is also a problem. You can expect one problem from this module. So go through all the formulas. Next is pre-emphasis and de-emphasis. This is also important to topic, where why do we need this pre-emphasis and de-emphasis? Because we are having a problem. What noise will affect the high frequency components of the message signal, and also high frequency message signal often have what lower amplitude, so that is more susceptible to noise. So to overcome this, we have a solution, that is pre-emphasis. It boosts the high frequency components before transmission using the high pass filter. So this is a circuit where we are having high pass filter. R and C is present. We are having frequency modulator. So hence we get a frequency pre-emphasis FM output. For that, this is a graph or the slope you can observe. This is a time constant. Let us consider it is 75 µs. So FC will be what? 1 by 2 pi t. That is on substituting we get 2123 hertz. Amplifies at the 6 decibels. This is amplified at the 6 decibel per octave. For the frequency what? For the frequency greater than this 2123 hertz. So next comes the de-emphasis. De-emphasis it is the reverses the pre-emphasis at the receiver using the low pass filter. At tau is equal to, we are considering a time constant. At this part here it reverses this process. It attenuates the high frequency signal at the 6 decibel per octave. So combined effect is what? The main thing here, where both we can observe. It restores the flat frequency response while enhancing the high frequency signal to noise ratio. You can observe if the FM is given in here, frequency demodulation is there. This is our de-emphasis circuit where we are having R and C. So we get the audio output. Okay, next is this is the slope you can observe for de-emphasis. As I said, combined effect, this will be our combined frequency response. Above will be the pre-emphasis frequency response and below will be the de-emphasis frequency response. This is a graph plotted against the frequency and amplitude at the tau is equal to 75 µs. Next is the next important question, that is frequency modulation versus the amplitude modulation. Here FM versus AM. Advantage of this here is advantages of FM, I will say, over the AM. First thing you have to know is it has better immunity to noise than the AM. Second thing, FM receives user limiter circuit to clip the amplitude noise, preserving the signal. It will preserve the signal, unlike AM. Amplitude is dependent, but here it uses the limiter circuit to clip the amplitude of the noise. Third thing is phase shift induces distortion, also has less impact. So phase shift actually induces the distortion, which has a less impact on the FM. Main thing you should know is capture effect. Capture effect is frequency receiver accepts the stronger of two signals. That is, if the two signals are there, it will accept the stronger one. Both of the same frequency, then it will reject the weaker one. It will accept only the stronger one. It requires only about 1 decibel difference. So 1 decibel difference also it will reject the weaker one, and the signal will dominate the stronger one. In AM, both the signals are heard simultaneously if one of them the same frequency, causing the interface. So example, while driving, you can a listener experience the switching between the stations. In the radio stations, when you are listening to the radio, there is a switching between the two stations, so that it always attempts to accept the stronger signal of the similar strength. Now the transmitter efficiency, here FM signals have a constant amplitude, so allowing use of the efficient class C amplifier is perfectly used. But the AM requires linear amplifier. For AM we require A or B class for the modulating fidelity less efficient. So high frequency AM uses high level modulation but becomes impractical at very high powers. Coming to the disadvantages of FM, what is over the advantages? So here, first thing is excessive spectrum usage. It uses more spectrum where frequency modulation is much more than the bandwidth than AM. Wideband FM, that is greater noise immunity but causes more spectrum is needed, obviously. Second thing is circuit complexity is more. Frequency division demodulation of the modulation circuit used to be complex than the AM. So today we are having ICs that is used to do this. They make them cheap and easy to use actually, but nowadays in the narrow band the maximum deviation is the 5 kilohertz, and the maximum modulation frequency is 3 kilohertz. So our deviation ratio will be 5/3, that is 1/1.67. FM limits to UHF, VHF and the microwave bands. Application of FM and AM. It is used in AM broadcasting radio, FM broadcasting radio, TV sound, FM stereo, multiplex, TV picture, TV color, cellular telephone, aircraft radio, and marine radio. So for your easy understanding, I have made two columns to compare the AM and FM based on the features. First is modulation method. So here amplitude of the modulation is varied, modulation signal is varied, their frequency is varied. Here the frequency is 535 kilohertz to 1605 kilohertz. There it is 88 megahertz to 108 megahertz. Bandwidth here it is narrow, approximately 10 kilohertz. There it is wide, that is approximately 2000 kilohertz, which is more immunity to noise, hence has more spectrum. This is already explained. Next is transmission distance, longer distance traveled by the AM, so hence used in the broadcasting. Here it is limiting range, so a line of sight is an example. Power consumption, here it is low, there it is high. Circuit is simple, circuit is complex. Capture effect, both signals are heard simultaneously if they have same frequency. But here in the frequency, it accepts only the stronger one and it rejects the weaker frequency. Transmission efficiency, this requires linear amplifier, that is A or B class for the modulation. Here we need constant amplitude allowing the use of only class A amplifier. So this was all about the part 1 of the module 3. I hope you got all the topics cleared. Please do watch the part 2 video, which is having a more important topics compared to this, where we will be discussing about modulators and demodulators. I hope the explanation and the structured notes made you a easier one. If you have missed the earlier modules from the module 1 or module 2, you can find the links in the description box below. If you find the video helpful, and make sure you like it, share it with your classmates, and subscribe to Exam Ignite to stay updated on all the upcoming parts and the solved papers. Thank you for watching. I'll see you in the next video.